Ok, en honor a la puntualidad vamos a ir empezando. Muchas gracias nuevamente con todos por su puntualidad y por participar de la charla de esta noche. Hoy tenemos el honor de oír al doctor Warren Caldwell, quien nos hablará sobre el ensayo geofísico de resonancia magnética para las aplicaciones en minería, geotecnia y geoambiental. Esta charla llega gracias al auspicio de las empresas Contec y Vista Clara. La empresa Vista Clara desarrolla y fabrica tecnologías geofísicas innovadoras basadas en resonancia magnética para investigaciones de aguas subterráneas, medioambientales y geotécnicas. Las tecnologías pioneras de Vista Clara incluyen el GMR, los primeros instrumentos NMR en superficie multicanal del mundo, Geolink, las que son las primeras herramientas de registro en perforaciones de pequeño diámetro, DART, las primeras herramientas de registro NMR portátiles y compatibles con empuje directo, y Harpton, las primeras herramientas combinadas con ensayos de penetración tipo CPT y medición NMR. Las tecnologías geofísicas de NMR de Vista Clara se utilizan ampliamente en investigaciones de alto valor sobre recursos de agua subterránea y remediación ambiental, y cada vez son en investigaciones geotécnicas de alto valor, incluyendo el sector minero. Las mediciones geofísicas de NMR permiten la determinación directa del contenido volumétrico del agua y la porosidad, así como las estimaciones cuantitativas confiables de la porosidad efectiva, la distribución de tamaño de los poros y la conductividad hidráulica. Estas mediciones ayudan a reducir la incertidumbre, los riesgos y, en última instancia, los costos en una amplia variedad de investigaciones del suelo. Recordemos que tenemos traducción simultánea, así que en la parte inferior van a poder ustedes oír la charla con la traducción en vivo y en directo. Al final, ustedes también podrán dejar sus consultas, si gustan, en el cajetín de consultas para poder nosotros ayudarlo al doctor Warren a responder. Entonces, sin más, empezamos. Dr. Warren, thanks for your time. You may begin whenever you like. You can share your screen if you want.
Very good. Greetings, everyone, and thank you for joining us this evening. This presentation will be on magnetic resonance geophysics and its applications. Can you hear me okay and see my screen?
Yes, we can see you.
Okay, very good. So my name is Warren Caldwell. I'm a geophysicist at Vista Clara, and I manage rentals and services. That includes customer training and field support. On the call, we also have our chief scientist, Daria Morozov. Daria runs our research and development at Vista Clara. So here's a summary of the topics we will cover. We'll start by discussing the principles of magnetic resonance and then go into some applications that we think are relevant for this audience. So magnetic resonance, nuclear magnetic resonance, operates by direct detection of hydrogen nuclei. It's the same physics as in medical MRI imaging, but in this case, we're using it in the ground or on the ground surface to detect groundwater in geologic materials. So it's worth noting that nuclear in the name refers to atomic nuclei. It does not refer to radioactivity. So sometimes clients or customers might be concerned about the fact that it has the word nuclear in the name, but the process uses only magnets and electricity, just as in medical MRI, no radiogenic materials. So the NMR signal, in a few slides, we'll discuss how the NMR signal is generated, but this is what the response looks like on the right. It has an initial amplitude and it decays over time. And the initial amplitude is proportional to the number of hydrogen nuclei that are in the measurement volume. So that is the volumetric water content. And then the rate of decay of the signal is proportional to the, or is related to the pore size distribution. And that's because, as shown on the left, when a hydrogen molecule interacts with a grain boundary, when it physically bumps into a grain boundary, the orientation changes, and that molecule, that excitation contributes less to the measured NMR signal as a result of that interaction. So the more pore wall interactions happen, the faster the NMR signal decays. So here's an illustration of what that looks like. In the center, you can see in the dark blue line, that represents a very slow decay, which is indicative of water in large pores. The light blue line is a slightly faster decay. That's indicative of water in medium-sized pores. And the brown line is water in very small pores, clay-bound pores, and that is a very fast decay. And in a real system, you would, of course, have a combination of pore sizes, some very small, some larger, and the measured NMR signal is the sum of those individual decays, and we call that a multi-exponential decay. So during the processing of the NMR data, we generate a T2 relaxation curve, which is shown on the right. And that is a continuous distribution of the T2 relaxation times that are observed in the raw signal. So that continuous T2 relaxation curve is binned into, in typical processing, is binned into three categories: clay bound, capillary bound, and mobile, based on empirical observations of typical materials. So in summary, NMR provides first and foremost volumetric water content, because it's sensitive to the number of hydrogen nuclei that are present in the measurement volume. If you know that the formation is saturated, then that also gives you the porosity. The NMR in itself cannot tell you directly whether the formation is saturated, so you would need some other information to be able to tell you whether the formation is saturated. And if it is, then the volumetric water content from the NMR is therefore giving you the porosity. The NMR also provides a relative pore size distribution, and because water content, porosity, and pore size are strong physical controls on hydraulic conductivity, there are several semi-analytical, semi-empirical relationships from the literature that relate measurements of or NMR measurements to hydraulic conductivity. So you can get estimated hydraulic conductivity or permeability from the NMR measurements, and also transmissivity. That works best, that estimate works best in aquifer materials, but people have applied it in all sorts of geologic materials, aquifer materials, semi-consolidated materials, and even in fractured rock. But again, the estimate of hydraulic conductivity, it's most quantitatively accurate in unconsolidated aquifer materials. So NMR in geophysics is typically applied in one of these domains: borehole logging, portable or direct push NMR, which it's the same type of probe, it's just deployed a little differently, and then surface NMR, which is quite different in that you are operating non-invasively from the surface, and you're using Earth's field instead of permanent magnets in the probe. There are a few other geophysical applications of NMR in core analysis and some other shallow surface instrumentation that we won't discuss here. So first we'll look a bit at how borehole logging NMR works. So as I mentioned, there are permanent magnets in the probe, and these create a magnetic field that polarizes the hydrogen nuclei. And then there's a wire coil, a copper coil inside the probe that is effectively it's an antenna. So it acts as a transmit antenna to transmit radio frequency pulses, electrical pulses that create a secondary magnetic field that alters the orientation of the hydrogen nuclei. And then that excitation transmit pulse is turned off, and the hydrogen nuclei return to their initial orientation. But as they do so, they create a um, uh, magnetic moment that induces a voltage in the coil that can be measured. So the more voltage that's measured on the coil, the more hydrogen nuclei are present in the measurement zone. So the uh, the process of making an NMR measurement with a borehole logging tool starts before the project even begins with a calibration process, or it's really a normalization or standardization. So the probe is placed in a tank of 100% water, and a measurement is made, and then whatever voltage is measured on the coil, we know that that indicates 100% water. So that standardization defines what is 100% water, and if there's 0 volts on the coil, then we know there's 0 water. So these four images here are from an NMR log, and these represent basically the four stages of NMR data. So on the left is the raw time series data, and in this depiction, the brighter the color, the more water content, and then the further that energy extends to the right, that means that it's a longer decay, which means water in larger pores. So the next panel over, the T2 distribution, is showing the same information, but in terms of the T2 distribution. So here again, the brighter colors are more water content, and the further to the right that energy is plotted, that again means water in larger pores. So the third panel here is the water content, and here it's color coded in the um, three different pore sizes that we saw earlier: clay bound, capillary bound, and mobile. And here between 210 and 230 meters, you can see we have the largest water contents and the largest pore sizes, and consequently also the highest hydraulic conductivities. So um, let's see that, and then between 100 and 150 meters, we can see there's very um, short signals, low T2, short T2 decay times. That's indicative of water that's in clay-bound pores, and we see that in the water content plot. And we can see that there's low hydraulic conductivity. So these four images, these four different plots are, in a way, they're showing all the same information, but just in depicting it differently. And so you can see the same features across all four plots. So the Vista Clara's borehole logging tools go by the product name Javelin. These are available in a range of probe sizes, designed for different sizes of borehole. And in the center, this is an illustration of the NMR measurement shells, and in this illustration, there are 3 of them. Some of our probes have 2 measurement shells, some have 3. In this case, 3 are shown. And one of the most powerful features of NMR as a geophysical logging tool is that the measurement takes place only at a finite distance from the probe. So the measurement is measuring only at the location of the shell. There's no sensitivity between in the area between the probe and where the measurement is taking place. So the probe effectively sees past the PVC casing or the annular space, any filter pack, and sees into the formation, as long as you're using the correct size probe for a given borehole. So that means that NMR logging is one of the few geophysical logging methods that provides meaningful information in cased boreholes. So one of the big applications for NMR logging is in the environmental remediation industry, where there may be networks of existing PVC cased monitoring wells. On the right here, this is an example of our processing software, and this provides all of the operations in the data processing and data analysis that we've seen on the previous slides. That's all built into this software, and that software is included with rentals and purchases of the equipment. Oops. So next we'll discuss the portable and direct push NMR tools. So the probe, as shown here in the center, the yellow probe here, the construction of the probe and the measurements it makes, it's the same as in the previous section. But the difference here is that the probe is smaller and the whole package is more portable. And some variations of this dart, so this is called the dart probe, that's our product. They can integrate with direct push drill rigs. So here's an example of a log from a direct push dart measurement. We can see at 20 meters and at 44 meters, there are some well-sorted sands. We have a high hydraulic conductivity zone between 30 and 40 meters. And then in the near surface, there are clays. And we can see that the clays are shown by the short T2 distribution, low hydraulic conductivity. The well-sorted sands have a long T2 time. And then the high hydraulic conductivity zone here has some of the longest T2 times. Also, there's another such zone here that's not pointed out, but of course between 47 and 53 meters, there's another zone of relatively long T2 decay times and high mobile water content, high hydraulic conductivity. So this direct push, or this dart system, is highly portable. It can integrate with direct push rigs, and that of course allows it to be deployed without having to drill and case a permanent borehole. You can get an NMR log in a location in a day and abandon the boring afterwards. So this is just an illustration of the deployment of the direct push system. So the uh, direct the direct push drill rods are driven into the ground, and then the probe is deployed through the rods after they've reached their total depth, and then the rods are retracted, allowing the probe to hang from the bottom of the drill string. And then NMR measurements are made as the probe is drawn to the surface. So NMR, I mentioned that it can measure through PVC casing. It can log in open boreholes in PVC casing, but it cannot log through metal. So that's why in this application, this direct push integration, the probe is suspended from the bottom of the rod string because the probe can't operate through the metal rods. So next, I'll briefly mention the surface NMR method. This uses, instead of permanent magnets that are in the probe, the B0 magnetic field is from Earth's magnetic field. And the method operates by laying out large loops on the surface, and then a similar excitation pulse as with borehole NMR is run through these surface coils, and then the same physical response in the hydrogen nuclei is generated and measured on the coil. So the advantage of this method is that there's no drilling required. It's completely non-invasive, and it provides essentially the same results, the same data products as the borehole NMR, with a few variations. There are some limitations to this method. It's very sensitive to electromagnetic interference, so you cannot be too close to power lines or infrastructure. It works best in rural locations. And if there is highly conductive ground, that will limit your depth of investigation. If there's high magnetic susceptibility, that can cause problems with interpretation. And if the water in the subsurface is in very small clay-bound pores, and then it can be difficult to detect those using this method. So I won't go into too much detail in the processing of surface NMR data. It's a bit different than the processing of logging data. Logging data is simpler in that the depth information just comes from the location of the probe, whereas the depth information with the surface NMR, you have to invert the data, do a geophysical inversion to project the data to depth. So as with any such inversion, the resolution decreases as you go deeper into the model space. And the results of a typical surface NMR survey or surface NMR sounding are shown on the right here. This decay time distribution, this is equivalent or similar to the T2 distribution that we saw with the borehole NMR. We have our log of water content. You'll note there's no clay-bound water in this depiction because that's not really possible to detect, or it's more difficult to detect with the surface NMR. And then we have our estimated hydraulic conductivity. So it's very similar data to the borehole logging NMR, but with a different vertical resolution because of the fact that it's operating from the surface and you're doing an inversion to get the depth information. So now here we'll go into some examples, some case studies, some applications of the technology. So there's a lot of interest and growing interest in using NMR for mine tailings. This is the illustration shown here is one of the early tests of our direct push dart NMR system that we did in Arizona with Contech. This project, actually, we did a series of direct push logs using this CPT truck, and those were adjacent to a borehole. You can see the PVC casing here next to the CPT truck. This was a borehole that was drilled, and 3-inch casing was installed, and this was logged with a traditional Javelin logging probe, and then that data was correlated or compared with the direct push result, and we got good agreement between the two. So in this example, we can see we're inferring that there's a water table at about 45 feet. Below that, you can see the overall water content, and the mobile water content is slightly higher. That's our clue that that's where the water table is located. And one of some of the interest in using NMR and mine tailings is to estimate void ratio for analysis of mine tailing stability. So here, this also mentions that the pore size distribution is derived from the NMR measurements. And in this example here, this is overall fairly low mobile water content was detected in this log here. We've also done logging in earthen dams, tailings impoundment dams. This is a tailings impoundment dam in Montana in the United States. So the objective with this study was that the mine operator was seeking to increase the height of their tailings dam, their tailings impoundment dam, and they were wanting to get more information about the materials and the condition of the dam. Limited records existed about the early years of construction, and the NMR was logged in a series of boreholes along with existing that data was combined with information from an existing piezometer network, and the objective was to look for evidence of perched water. We also have there's a NMR logging system that's being used in Yanacocha gold mine in Peru that has been operational since 2023. I'm not Vista Clara is not involved in any of the analysis of that data, and we can't really speak to how it's being used. Some of you on the call may be more familiar with the work that's being done at Yanacocha than I am. So I don't not able to show any data or any results here, but just wanted to mention that work is being done. NMR is also used in brine mining, solution mining, lithium production. So SQM in Chile has been using Javelin systems for many years now in multiple applications. They use it for optimizing well construction, and most importantly for estimating resource size, because the NMR provides effective porosity, and they combine that with their estimates of mineral concentration, and that provides an estimate of resource size. So NMR, I mentioned earlier, it is used in the environmental remediation industry. Um, for the purposes of high-resolution site characterization and development of conceptual site models. This is an example from Nevada in the United States. Is a There was a factory that exploded in the 1980s and released a lot of contamination into some of the local waterways. So there's a large environmental cleanup effort. And in yeah, around 2018, 2019, a lot of the wells in this area were logged with uh, NMR logging tools, and that information about the hydrogeology was used to inform um, the groundwater flow model for that was used for mapping contaminant flow and understanding groundwater migration in the contaminated zone. Here's another example of high resolution site characterization. This is a direct push NMR log. Here you can see there's a fairly large change in the aquifer properties just below 10 meters. Above 10 meters, we have uh, very long signals, high mobile water content, high hydraulic conductivity. And then below 10 meters, the overall water content is similar, but the pore sizes are completely different. We have short T2 decay times, and uh, that's therefore indicative of water in very small pores, very low hydraulic conductivity. And the other feature of this study was that some HPT profiling was done in this location as well. And HPT, this hydraulic profiling tool, it provides a physical measurement of hydraulic conductivity. So the strength of that compared to the NMR is only estimating hydraulic conductivity. The HPT tool is physically measuring it. So that is preferable in some ways, but it has a limitation in that there's an upper limit to what it can detect because of the limitations of how fast it can inject water, how much pressure it can generate. So it's limited to estimating an upper limit of about 30 meters a day that can be measured with the hydraulic profiling tool. Whereas NMR, it can estimate much higher hydraulic conductivities. So here we're estimating um, almost, well, depending on which method you use, 100 to potentially up to 1,000 meters per day. These different curves here, SDR and SOE, are different uh, methods for estimating hydraulic conductivity that make different assumptions. I mentioned these relationships are kind of semi-analytical, semi-empirical, and they make different assumptions about how the NMR relates to um, hydraulic conductivity. So some may be more or less appropriate in different situations. These multiple methods exist in the literature, so we include them both in our software. Next, we have a geotechnical example. This is a large infrastructure project from the United Kingdom. This was actually done in a river on a jack-up barge. And the objective was to characterize the sediments for future tunnel construction, and allow them to plan their dewatering. Excuse me. And this provided the information that they needed for their work. For time, I'm probably going to skip some of these examples of surface NMR. This is an example of a DART survey, and here you can see that one of the advantages of the DART is because of its size, because of its portability, you can access remote locations, as shown here. We hiked the system into these locations, and then we were also able to return over a period of a year and a half and make measurements in different locations in this drainage basin, in different conditions. So at the BC top location, there was not a significant change through the seasons. At the Willow location, the lowermost location, there there was a significant change between the seasons. So more mobile water content in early summer than in late fall. So this kind of spatial and temporal information was made possible by having this portable system that allowed easy repeat measurements and easy access to these locations. So here are some examples of NMR being used in kind of novel ways in remediation, in environmental remediation. So biofilms or biofouling can be used to block pores and impede water flow, and that can be measured by NMR because the pores are smaller, the T2 distribution is shorter, and that was exactly what was detected in this project. You can see as time goes increases here, the T2 time decreases, and then it reaches a baseline after about 5 days, and then a solution to kill the biofilm was injected at day 14, and the T2 time then returned to its original state. So this is a similar example with precipitation of a material that's again intended to block groundwater flow. So this is at a former uranium mill site in Utah, and the uranium left over from the mill operations is migrating into a local river. So this was an experiment undertaken by the Department of Energy to or yeah, undertaken by one of our national labs to precipitate this hydroxyapatite material that would impede groundwater flow. So here you can see in these red boxes, the blue curves are before the injection of the material that's going to precipitate and block the pores, and then after the injection, you can see there's a significant drop in the hydraulic conductivity. This is hydraulic conductivity is plotted here. So significant decrease in permeability can measured with NMR as a result of these active remediation efforts. So just a few more slides, and then I do want to leave some time for questions. This is a new tool that we are in the process of finalizing. This combines CPT with NMR into a single tool. So your typical CPT measurements are done by the CPT cone, and then there's a non-metallic section of this probe that will make NMR measurements. So CPT measurements are done on the way down, and then the probe is withdrawn and NMR measurements are made on the way up. And again, all of your typical CPT and NMR data products can be obtained with a single tool in a single logging operation. Here are some examples of that tool in action with the NMR data on the left and the CPT on the right. And here we're identifying some silts and clays and some interbedded sands in the mix there as well. I'll keep moving and try to finish up here. Here's another example of this tool in use. This is a fairly homogeneous log here. You do have more clay-bound material through the middle of the log, but then there are a few sections with some longer T2 times, some more mobile water content that are indicating some sands, and that can be picked out in the data here. So that is everything from us. We would welcome any questions from anyone. Thank you all for being here.